Hello all, I welcome you once again in the series of discrete mathematics paper, and in this lecture I will discuss about the Euler and Hamiltonian graphs, right? This is your unit 3, right? And I have already covered in my previous video about this representation of graphs, adjacency matrices and lists, also the isomorphism. So in this I will discuss about this connectedness, in which I will discuss about the paths, circuit and cycles, what the difference these between these, and I have already completed bipartite and complete bipartite, right? And then I will cover this Euler and Hamiltonian graphs, right? This unit 3, right? And before that I have already covered the basic properties of graphs, in which I have discussed about the various types of graphs and all, right? So let's start this, right? So I will start from the topic of where I have left, of isomorphic and complete bipartite, and after that, so I begin with this your circuit, right, or path. So first of all, what is a path? So a path is a sequence of edges, right? What is a path? Is a sequence of edges, is a sequence of edges that begins at a vertex of a graph, right? At a vertex of a graph. You know what is a vertex? It is basically a node, right? Okay. Graph, and travels from vertex to vertex along the edges of the graph, along the edges of the graph, right? Along the edges of the graph. Sorry. So here I have this right example for you. Let's understand by the example that I have this example. This is your graph, right? This is a graph because it has edges and vertices, and this is like, right? So this vertex is connected to this, right? This is your A vertex, this is your B, this is C, this is D, this is F, and this vertex is F. So B is connected to, right, F, and D is connected to C, right? In that way, D is connected to C. So this is a graph, right? Very simple graph, right? So if I need to find a path of length 4, right? A path of length 4, right? Between, right, A to E, right? But A to E. A to E will be A to B, right? A to B, then B to C, then C2, F, then F2, right? So this, if I use this color, I don't know what's happening here. Okay, no problem. Okay, so here I can, okay, I use like this direction. So A to B, right? A to B, then I go B to C, then I go to C to F, then I go to F to E. This is of length 4. I can also go directly from A to E by covering only this one edge. So this is because they have asked of length 4, so this is one length. Length means the distance between the two adjacent vertex is measured as 1 unit, so or one step, right? So this is one, this is the second step, okay, and this is the third step and the fourth. So that's why this length path is 4. So from A to E we go like this, in this way, right? Okay, so this is a simple path. Why is the simple path? Because there are these are the edges between these. When we travel from A to E, there are edges. Okay, so consider this another path. Okay, the path is D. Okay, let me write from this side, right? That was your 4. So let's me write here. This is D, E, C, okay, A. If I write this, so this is not a path, right? This is not a path. Not a path. Why it's not a path? Because when we move from D, you are here and you are moving towards E. Yes, it's okay. When you're moving E to C, so I don't have any direct path from E to C, because if I want to go from E to C, I have two ways, from E to B and then B to C, and then second is E to F, then F to C. So there is no direct edge, but they are saying that they have gone as like D to E, then E to C, and then C to A. So because it's not a path, because there is no edges, there is no edges between E to C. So that's why it's not a path. It's just for your example, and please do remember this concept of path, right? Because when we when I talk about the Euler path and Hamiltonian path and Hamiltonian Euler circuit and Hamiltonian circuit, we must remember these small concepts of simple path or the circuit or right, simple graph and multigraph and all. So once you know that these concepts, you will be right, you will be it will be easy for you to grasp those concepts, right? So here the connected components, when I talk about the connected components are the, sometimes we have the different components, like this is like here I have this component, right, A, B, C, right, and here I have another component of this graph which is like this, okay, right, D, E, F. So this is a graph, okay, this is a graph, but it has two components. These components are not connected to each other, but this is a graph, okay, this is a graph G having two components, right, but these are not connected to each other, okay. So likewise, this is the concept of components of a graph, right? So we have these types of graphs also when, right? Now I talk about your circuit, right? So a circuit is like this in this example, this previous example, we have a circuit, right? Circuit means your means circuit cycle, right? So what do you mean by a circuit, right? So path is the just the edges for all the vertices. So when we start from a vertex and go to another vertex, there must be an edge between these two vertices. So we say that, yeah, there is a path. So if that path, if I start from A here and traveled through these all the vertices and I end on A, then it will be like your circuit, right? Okay, now we understand the concept of Euler graph, right? Euler graph or Euler path or Hamiltonian path, right? So let first I write the definition of Euler paths, right? Because in exams they ask you about this, right? So an Euler path in Z is a simple path containing every edge of G, right? What is an Euler path? An Euler path in G is a simple path, right? Is a simple path containing every edge of G, right? Okay, so this is the definition for Euler path, right? Okay, and what is an Euler circuit? Okay, Euler circuit. So you know what is a circuit if the starting and ending vertex are the same. Okay, so it means there is a circuit, right? Okay, Euler circuit is an Euler circuit in a graph G. Okay, in a graph G is a simple circuit. Is a simple circuit, right? Containing every edge of Z, right? Okay, so now the concept of Euler path and circuit are like so I draw a simple graph for you, right? And we will find that which one has an Euler circuit and which one has an Euler path. Okay. Now, so we have this figure for you, right? Just I'm taking this example, right? The example is so. Okay, so for example, this is your example, right? So I have these vertices A and B, right? And here I have this vertices E, right? And here we have these numbers are D and C. So this type of graph, in which if there exists in a cycle or not. So in G1 we can say easily that if I travel from A, then we go to E, right? Then we go to C, right? A, E, C, then D, then E, then B, then A. Okay, right? So A to C, A to E, then E to C, right? Then C to D, okay, and then D to E, then E to B, and then B to A, right? So in that case we can find that there is an Euler circuit, because according to the Euler circuit definition, that in a graph is a simple circuit containing every edge of C. So they have covered all the edges, right? So in that way we have covered all the edges. So this is an Euler circuit, example for Euler circuit. Okay, in exam they say that find an Euler circuit, Euler path. So you must keep in mind the basic difference between the Euler circuit and between the circuit and path. So first of all, these two definitions must be clear. So I just told you in the starting of this video that what is a path and what is a circuit, right? Okay, now take another example. The example is this is a graph, right? And do remember these definitions of Euler path and circuit, because they are going to ask in your exam, and okay. Yes, so here we have this this graph, right? So we have A, right? A, B, E, E, D, and C, right? Okay, this is your graph. So let's say this is G2, right? So in G2 graph, ठीक है, in G2 graph we don't have an Euler circuit, because if I start from A, I go to B, then I go to E, then I go to C, then I go to D, then A. So in any way, right, in any ways it's not possible that we cover all the edges, because in the definition they say that an Euler circuit in a G is a simple circuit containing every edge of G. So if you start from here, you will come back here, but will not cover the all the edges in a graph. So right, so that's why G2 has not an Euler circuit, right? So this is the example for Euler circuit and, right, Euler circuit and, or because in this graph it has an Euler circuit, right? But this graph is example of not having an Euler circuit. So please keep in mind the difference. Okay, now we move to another, right, another concepts. So path is very simple. If you find a path, then it is very simple, right? Okay. Now let's take an example for the example for Euler path, right? So that you can better understand the concept of Euler path. And then I move to the Hamiltonian path and circuit, right? So let me draw a graph for it, right? So now this is your graph, okay? This is a graph. I have A, B, C, D and E. Okay, now you see here that it has an Euler path, है ना? So first of all, for a graph to have an Euler path, it must cover all the, right, what, all the edges of G. Another path in G is a simple path containing every edge of G. So is that possible? In that example we are covering all the edges. So let's find. Okay, let's find if we can find a path, right? So start from A, right? A to C to D, right? Okay, then B, right? Okay, can we go right? We can go right. A, C, then D, or then E. Let's say then E. Okay. So we have covered this vertex, this edge, and this edge. Okay. Now we go back to this, right? E, and then B, right? Then I have covered this, right? Then to D, right? Okay, then this one, right? B to D, and then A, right? And then B. So in that way, right, we have covered all the edges in this graph, right? So this graph, let's say is G3, contains a Euler path, right? Euler path. So does it contain a circuit, Euler circuit, or not? Because in an Euler circuit, it must cover all the edges which it has already covered in this example, but it comes back to the same vertex or same starting vertex. Means, समझ रहे हो आप? तो पाथ क्या है? पाथ में आपको सारी एजेस कवर करनी है ना, कवर ऑल द एजेस. But it's not necessary that the initial vertex will be your end vertex. So you start from that vertex and you cover all the edges and come back to this vertex. It becomes a circuit, right? It becomes a circuit. But if you cover all the edges, okay, all the edges, but you don't reach to this, so this is your path, right? This is your path. So in path it's not necessary initial or end, but in a circuit the definition is same, like you have to cover all the edges, but your starting vertex and ending vertex, starting and ending will be same, right? So that's why we are saying that it has a path, but not circuit, because for circuit there is a necessary condition, okay, that it must be that when you start from a vertex, you must end by covering all the edges to that particular vertex. So it's not the case here, right? So I think this concept is very much clear to all of you, right? Okay, now we go back to the Hamiltonian, right? Hamiltonian circuit and path. Okay, so first of all we must know that what is an Hamiltonian path and Hamiltonian circuit. But before that, there are two theorems that they might be asked in your exams, right? Based on this concept of Euler path and circuit. So I discussed with these two theorems, right? So first theorem is the theorem one is a connected multigraph. So you know that what is a multigraph. If you don't know, please watch the first videos in the series of discrete mathematics. A connected multigraph with at least two vertices has an Euler circuit, right? Euler circuit. And you know what is an Euler circuit, okay? If and only if each of its vertices has even degree, right? ठीक है, तो ये थ्योरम कहती है, इट सेज दैट कि एक कनेक्टेड मल्टीग्राफ with at least two vertices has an Euler circuit if and only if each of its vertices has even degree. ठीक है, तो हर एक वर्टेक्स की क्या होना चाहिए? even degree. so एक मल्टीग्राफ के लिए जिस पे क्या है, with at least two vertices, जिसके कम से कम दो वर्टिसेस हैं, उस ग्राफ में एक आइलर सर्किट है ना, और आइलर सर्किट एग्जिस्ट करता है. इट फॉलोज द डेफिनेशन ऑफ आइलर सर्किट ओनली, है ना, ओनली व्हेन इफ ईच ऑफ इट्स वर्टिसेस हैज इवन डिग्री, राइट. So for example, right, for example we have this Kongsberg bridge problem, right? So okay, so you must remember this, right? So you must remember this definition or theorem, that what is it, right? Okay, now the second theorem is, and I will definitely solve some questions based on these theorems, right? Questions means that I will prove, no, with proof that what are the examples of the examples on these two theorems, right? So the second theorem says that a connected multigraph has an Euler path, but not an Euler circuit, right? But not an Euler circuit. If only if and only if it has exactly two vertices of odd degree, right? Two vertices of odd degree, right? Okay. So here if I, for an example, if I take this simple graph, right? This is a graph, right? Let's say A, B, C and D. Okay, so it has an Euler path. Euler path क्या है? When I start with this, right? So I must be covering all the edges, right? So I go to A to B, right? A to B, or you go from right? Okay. You go from A to C, right? Then C to D, right? Then so here you started from A to C. You have covered this, right? You have covered this. Then you go to B. You covered this. You go to this. You covered this, right? Okay. So as it has an Euler path. So in that way we are not covering this one. So let's find another. Okay. So let's find another path. Another path is your if I start with D, right? I start with D because I can start from anywhere, because I have to find a path that must cover all the edges. So I start with D. Okay? I start with D and then go to A, then go to B, then C, right? Then D and then B. Okay? So D to A. Okay, sorry. Wait. So A, B and okay, I have just numbered it, right? So A, B and C and then it is D, right? So now I can go, right? D to A. First I go D to A, then A to B, right? Then A to B and then B to C, right? Then C to D and then D to B, right? So I start from this place and then I go to like that. So that was my starting point. So in that way I am covering all the edges. Remember that edges must not be repeated. You cannot traverse or you cannot visit the same edge again. So in that way I am covering all the edges without repeating any edges. So it has an Euler path, right? And the definition of the theorem is proved because it has an Euler path but not an Euler circuit. If only it has exactly two vertices of 1 degree. Here if I write the degree of each vertices, so the degree of A will be is 2, degree of B is 3, degree of C is 2, sorry, degree of D is 3. So according to this theorem it must have two vertices of odd degree. So these are the two vertices B and D. B and D has odd degree because it is 3. 3 is an odd number, so it has two vertices of odd degree, right? So we can say that when this is the condition, so it has an Euler path. So there exists an Euler path in that case when two vertices are of odd degree. Okay, so these are the two theorems and on the concept of this Euler path in circuits. I hope that it will be helpful for you, right? So thank you.